Hello students, welcome to the video solution of day 11 Thursday questions on network theory. So these questions are on the Thevenin's and Norton theorems. These are very important theorems for GATE paper because GATE examiners used to keep one or two questions in every GATE paper related to these theorems. These are very important theorems on this topic of network theory. So first of all, let's look at what are these theorems, and then I will explain you the solution of the questions that I have kept in the paper in the series. Okay, now what is Thevenin and Norton theorem? Okay, suppose you have a big network. A big network is connected. This is a very big network, is connected to a variable load between terminals A and B. Okay, now every time this RL changes, obviously the current in this load RL will also change, and obviously the voltage across this RL will also change. So every time this RL changes, you have to solve this whole circuit again and again. So it is very difficult to do that. So to solve this issue, we used to replace this whole big network between terminals A and B by a series combination of VTH voltage and resistance RTH between terminals A and B. Okay, so we can say that this is the equivalent of this big network between terminals A and B. Okay, so if we have a big network between terminals A and B, it can be replaced by a simple series combination of voltage VTH and RTH as seen in the figure. Okay, now easily we can connect RL variable load here and calculate the current and voltage across this RL easily whenever it changes. Okay, so converting this big network to this combination of series VTH and RTH is done by Thevenin's theorem. Okay, so using Thevenin's theorem, we can replace or design we can replace the whole big network between two terminals A and B by a series combination of VTH and RTH. Now let us see what is VTH and RTH. Okay, so suppose this is a big network and these are the terminals A and B. Okay, and we have to find the Thevenin equivalent between terminals A and B, and the Thevenin equivalent will be like this. Okay, so to find VTH, what we will do, step 1 is open circuit the terminals A and B. Okay. Step 2, find out the voltage VAB, that is the voltage seen between these two terminals. Okay, so VTH is equal to VAB. Okay, simple. Just open circuit between A and B terminals. If there is any connection, any resistance or anything connected between A and B terminals, remove that and then find the voltage VAB between the two terminals. Okay, now to find RTH, there are two cases. Okay, case 1, there are no dependent source. Okay, there are no dependent source in the circuit. Okay, dependent source means the source in which the output is depending on another value of current or voltage in the circuit. So there is no dependent source in the circuit. Then simply remove all the independent sources okay, simply remove all the independent sources and find resistance seen between the two terminals A and B. Okay, now how to remove these independent sources? What are the independent sources? There are two kind of sources: voltage source and the current source. Now how we remove the voltage source? We remove the voltage source by short circuiting it, okay, and we remove the current source by open circuiting it. Okay, we remove the current source by open circuiting it, and voltage source is removed by short circuiting it. Okay, now let's look at case 2. Okay, now let's look at case 2. So the case 2 is when the circuit has dependent sources. Okay, when the circuit has dependent sources. So in this case we will do this. Step 1, remove all independent sources. Okay, remove all the independent sources. Okay, step 2, apply voltage VO between terminals A and B and assume I0 is a current flowing out of V0. Okay, step 3, find out VO divided by IO ratio. Okay, now RAB is equal to RTH is equals to VO upon IO. Okay, so this is the method, simple methods. Okay, so I'm just repeating it again. To find out VTH, open circuit the terminals A and B and find out VAB voltage. Simple. Okay, that is our VTH. To find out RTH, there are two cases. Case 1 is there are no dependent sources in the circuit. Then we will simply remove all the independent sources and find out RAB. Okay. Case 2, When the circuit has dependent sources, we will remove only the independent sources. Dependent sources will not be removed. Okay. Now apply voltage V0 at the output or between the terminals A and B. Find out current I0 is flowing out of this voltage V0. Find out the ratio VO upon IO, and that is your result of RTH. So using this, we can easily convert any big network between terminals A and B, okay, into this combination. Okay. Now, as we know what is source transformation, then using source transformation, we can convert this into a parallel combination of a current source and a resistance. The resistance will be RTH and the current will be VTH upon RTH. Okay, so this is actually the Thevenin equivalent. Okay, and this is with Norton equivalent. Okay, and this is called the Norton current. Okay, this is called the Thevenin voltage, Thevenin resistance. This is called the Norton current and the Norton resistance. We can see that the Norton resistance and the Thevenin resistance are same, exactly same. And we can see that the Norton current is equal to Thevenin voltage divided by the Thevenin resistance. Okay, one more thing, we can add one more thing here. Okay, so we can see that the Norton equivalent is this big network okay between terminals A and B. So the Norton equivalent is a Norton current IN and the Norton resistance RN between terminals A and B. Now we know that this RN is equal to RTH. So the method to find out RN is same as RTH. Okay, the method to find out IN or the Norton equivalent Norton current is VTH upon RTH. But let me tell you the method to find out IN separately. Method to find IN, the Norton current. Step 1, simple, short circuit the terminals A and B, short circuit them. Step 2, find out the current flowing in the short circuit between A and B. IN is equal to the current flowing in the short circuit A and B. Okay, so we know how to find IN, we know how to find RN. So this is Norton equivalent and this is your Thevenin equivalent. From Thevenin equivalent you can easily convert into the Norton equivalent. Okay, so now let's start solving the questions. Okay, so this is the first question. We have to find the Thevenin equivalent of the circuit in the figure. Okay, so let me copy the figure first, question first. Okay, so we have to find the Thevenin equivalent between terminals A and B. Okay, so to first of all to find VTH. Now to find VTH, we simply find the open circuit voltage between terminals A and B. So VAB is equals to question mark. Okay, now let's solve the question. Now suppose that this is grounded in the circuit, B terminal is grounded. So as we can see that here the voltage is Vx at this node A. Okay, and one more thing we can see that between these two terminals A and B terminal, this 2 Vx voltage is applied. So we can say that at B node we have voltage 3 Vx. Okay, now the current in this 2 ohm resistance is 0 because it is open circuited. Is it okay? Now let's uh, now now we can see that the voltage across this is 3 Vx. Okay, so the current in this resistance will be Vx by 2. Okay, because 3 Vx is the voltage, 6 ohm is the resistance, so Vx by 2 is the current. Okay, as we can see that the voltage across this 2 ohm resistance is 2 Vx, so the current here will be Vx because 2 Vx divided by 2 ohm. Okay, here the current will be Vx by 4. Okay, now applying the KCL at node B, we can see that here the current is 0, here the current is 3Vx by 2, 3Vx by 6, that is Vx by 2. Here the current is Vx, so the total outgoing current at node B is Vx by 2 plus Vx, that is 3Vx by 2. So the incoming current, that is this current, is equals to 1.5 Vx. Okay, so at node A, KCL we can see that the incoming current is 5. So incoming current is 5, we will write it minus 5. The outgoing current is Vx by 4, so plus Vx by 4. The outgoing current is 1.5 Vx. The incoming current is Vx is equals to 0. So we can say that 5 is equal to Vx by 4 plus 3Vx by 2 minus Vx. Let us say 4 as common. So Vx plus 6Vx minus 4Vx is equals to 5. So 3Vx by 4 is equals to 5. Vx is equals to 20 by 3. Okay, so Vx is equals to 20 by 3, and we can easily see that the voltage between A and B terminals is equal to the voltage across the 6 ohm resistance, because across 2 ohm resistance there is no current, so there is no drop of voltage. So we can say that VAB is equal to 3Vx, that is equals to 20 volts. So we can say that VTH is equals to 20 volts. Okay, now we have VTH. Now we will solve for RTH. Now as we can see that there is a dependent source in the circuit. Okay, so we will solve for case 2. Okay, now there is a independent source also, so independent source will be removed and we will draw the circuit again. Minus plus 2Vx okay. Now between A and B terminals we will apply a battery of V0 and assume that this is A terminal, this is B, and assume that the current flowing outside is I naught. We know that RTH is equals to V naught upon I naught. Okay, so we can see that at this node A, this is node B, the voltage at, we say that this is grounded. Okay, node A is at Vx voltage, node B is at 3Vx voltage. Okay, because this is Vx, this is 2Vx, so this is 3Vx. Okay, current here will be Vx by 2, current in this branch will be Vx by 4, current in this branch will be Vx, because the drop across this 2 ohm resistance is 2Vx, right? Now we can see that since here the current is at this node, here the current is incoming is Vx, the outgoing is Vx by 4, so easily we can say that the here current will be 3Vx by 4. Okay, clear? Again, incoming current is Vx, outgoing current is Vx by 4, so here outgoing will be 3Vx by 4. So here the current coming is 3Vx by 4. I have to add a page. Okay, now here we can easily see that at node B, the incoming current is, we can see that I naught is the incoming current. Here we can see that the current here will be 3 by 4 Vx. Okay, we have seen that. So the incoming current is 3 by 4 Vx is equal to the outgoing current. So let us see the outgoing current. So this is the outgoing current, Vx by 2, and this is the outgoing current, that is Vx. So Vx plus Vx by 2. Okay, so I naught is equal to 3 by 2 Vx minus 3 by 4 Vx. Okay, so this is 1.5 and this is 0.75. So this will give us 3 by 4 Vx is equals to I naught. Okay, now another thing that we can see that here is, if we apply a KVL loop in this loop, we can see that V naught is equal to the drop across this 2 ohm resistance, that is 2 I naught, and the drop across this 6 ohm resistance, that is 3 Vx. So V naught is equals to 2 I naught plus 3 Vx. Putting the value of I naught, we can see that V naught is equals to 1.5 Vx plus 3 Vx, that is 4.5 Vx. Okay, now we can see that V naught, we have V naught and I naught in terms of Vx. So V naught upon I naught is equal to 4.5 Vx divided by 3 by 4 Vx. Okay, so this will come out to be 4.5 into 4 divided by 3, 9 into 2 divided by 3, that is 6 ohms, is equals to R naught. Okay, so we can easily see that this is your RTH, that is 6, and VTH is equal to 20. Okay, so we have solved the question. Now let's move on to the next question. Okay, so here we have to find out the Norton equivalent between terminals A and B of the circuit. Now let's solve this question number 2. Here we have to find the Norton equivalent of the circuit. So now we know how to find the Norton equivalent. Okay, so to find out the Norton current, okay, to find out the Norton current, we will short circuit these two terminals A and B and find out the current flowing to through this short circuit. We short circuit A and B terminals. Current is IN. Okay. Now let's solve the circuit to find out this current IN. Okay. I think I have to like make a bigger circuit. Okay. So to solve, so I short circuit them and the current is IN. Now we can see that since this is the drop, this voltage is V0, so this voltage is also V0 because these two terminals are short circuited. Okay, so this 2 ohm resistance and 3 ohm resistance are in parallel. Okay, so now we will redraw the circuit by source transformation between 18 and 6 ohm resistance. Okay, so we can draw it like this. Okay, now but since 3 and 2 ohm resistance are in parallel, so it is 3 plus minus VO 2 0.25 VO. Okay, now I have this rotated the circuit, this portion to in like this in the clockwise direction. So this is terminal A and this is terminal B and this is current IN. Okay, for simplicity. Now let us say that this terminal is grounded and this terminal is at V0 voltage. Okay, so we can see that this is the incoming current. So incoming current at this node is 3. The outgoing current here will be V0 by 6. The outgoing current here will be V0 by 3. The outgoing current here will be V0 by 2. The incoming current here is plus 0.25 V0 is equals to 0. Okay, so we can say that 3 is equals to V0 by 6 plus V0 by 3 plus V0 by 2 minus V0 by 4. Let us take 24 as the common factor. So here we have 4 V0, 8 V0, 12 V0 and 6 V0. Okay, so we have 18 V0 by 24 is equals to 3. So V0 is equals to 24 into 3 divided by 18. So this will come out to be V0 is equals to, this will cancel, V0 will come out to be 4 volts. Okay, so V0 will come out to be 4 volts. Okay, so this is 4 volts. Now here we can see that the current in this direction will be 4 by 6. Current in this direction will be 4 by 3. 4 by 3. Current in this direction will be 4 by 2. And current in this direction will be that is 4 by 4. That is 0.25 V0. That is 1. Okay. So we can see that here the incoming current is 2 amperes. The outgoing current here is 1 ampere. Okay, we can see that now outgoing current is 1 ampere. Here it is 1 and here it is 2. Okay, so at this node, if we apply a KCL, then we can see that since the incoming current is 2, here the outgoing current is 1, so the current in this branch will be 1 ampere. Okay, so we can see that the current between A and B is equal to 1 ampere. Or we can do it like here also, that since we have solved for V0, so we can see that between these two terminals we have V0 voltage, that is 4 volts. So the current in this branch will be 2 amperes. At this node, that is current is in this direction is 0.25, that V0, that is 1 ampere. So the current in this direction will be 1 ampere. So we can solve here also after finding out the value of V0. Okay, so we have solved, that is IN is equals to 1 ampere. Clear? Now to find RTH or RN, they have same method. Okay, now let me copy the figure. But it will have lot of this. Okay, so I will copy it from here. Okay, I need to add pages, at least 2. Okay, so now let's solve for RTH. Now as we can see that since the circuit has a independent source and a dependent source, so case 2 will be applied here. Okay, we will apply a voltage at the between terminals A and B. So let us say that we apply the voltage that is equals to, since V0 is already present in the circuit, we cannot apply V0 at the output because it will create confusion. So we will apply VAB voltage and assume that the current here is IAB. Okay, so RTH will be equal to the ratio of VAB upon IAB. But the thing is, we have to first of all remove this 18 volt source. So 18 volt source can be removed by short circuiting it. Okay, because it's a voltage source, it is independent source, so we have to remove it. We will remove it by short circuiting it. Okay, voltage source are removed by short circuiting. So the circuit will become like this. Because I have short circuited this 18 volts. Okay, V0 by 4. Okay, so between A and B terminals I have applied a battery of VAB and I have assumed that the current is IAB. Okay, now we can see that since voltage across this 3 ohm resistance is V0, so here also it is V0 because they are in parallel. So the current here will be V0 by 6, current here will be V0 by 3. Okay, so here also the incoming current is V0 by 4. So at this node, let us say it is A node, this is B node. So at node B, the incoming current is IAB, the outgoing current is V0 by 4. So the current in this direction will be IAB minus V0 by 4. Is it okay? Now at node A, we have the incoming current, that is IAB minus V0 by 4. The incoming current is V0 by 4. The outgoing current is V0 by 3. The outgoing current is V0 by 6. Okay, so these two will cancel out. We can say that IAB is equals to, if we take V6 as common here, so we will come out to be V0 by 3 plus V0 by 6 is equals to V0 by 2. Okay, so we have IAB in terms of V0. Okay, now IAB equals to V0 by 2. Now let us apply a KVL in this loop. Okay, so we can see that KVL in this loop. VAB is equals to drop across this 2 ohm resistance and drop across this 3 ohm resistance. So drop across 2 ohm resistance is 2 into IAB minus V0 by 4 plus V0. Okay, because 3 ohm resistance has a drop of V0. So we have a relationship between IAB and V0. So it is 2 times V0 by 2 minus V0 by 4 plus V0. 2 times V0 by 4 plus V0, that is 1.5 V0 is equals to VAB. Okay, so now we have IAB and VAB in terms of V0. So we can say that VAB upon IAB, that is equals to 1.5 VO upon 0.5 VO, that is 3. Okay, so that is your RTH. So RTH is 3 ohms and IN is equals to 1 ampere. So the equivalent of this circuit is between A and B terminal is 1 ampere in parallel with 3 ohm resistance. Okay, so this is the equivalent between A and B terminals, the Norton equivalent. Okay, by if in the same question they ask us what is the Thevenin equivalent, we can convert it by source transformation. We can see that the Thevenin equivalent will be 3 volts in series with 3 ohm resistance by simple source transformation. Sorry. Okay, now let's move to the third question, that is we have to find the Thevenin equivalent of the circuit in the figure. Okay, so let's do it. Now this question I have kept to tell you a very important point, that first of all, if we look at in the circuit, we can see that there is no independent source. Okay, there is no independent source in the circuit. Okay, all are the dependent sources. This is also a dependent source, this is also a dependent source. Now when we will find, we can easily see that when there is no independent source in the circuit, then the Thevenin equivalent voltage VTH and the Norton equivalent current IN both are 0. Okay, because there is no one to flow this current I0 or V0 in the circuit. Okay, so until and unless I0 and V0 are not present, then these sources, these dependent sources are inactive. Okay, so someone has to initiate these current and voltages inside the circuit, then only these dependent sources will start providing the power to the circuit. So since there is no, until and unless, if we see that the circuit has no independent source, then clearly the first step is VTH and the Thevenin or Norton current IN both are 0. That's the first step. Okay, so in the Thevenin equivalent we can see that we do not have to find out the VTH, it will be 0 because there is no independent source. Okay, now let's solve the circuit. Okay, since I have to copy the figure, so I am rubbing all these things. Okay, so now let me copy the figure. Okay, now we have to find only RTH. We have to find only RTH. Okay, now to find RTH we will apply a voltage VAB and assume that the current here is IAB. Okay, now as we can see in the question, we will just solve the question and we will find out we have to find out the ratio of VAB upon IAB to get the answer. Now here the incoming current is IAB. Here at this node A, the incoming current is 0.1 I0. So the outgoing current will be, here we can see that since the voltage drop across this 10 ohm resistance is V0, so the outgoing current should be V0 by 10. So the first equation is KCL at node A. Incoming current is IAB. Incoming current is 0.1 I0. Outgoing current is V0 by 10. So this is the first equation. Now another thing that we can see that is, if we apply a KVL loop in this, we can see that VAB is equals to the voltage across this 10 ohm and voltage across this 20 ohms. So that is equals to V0 plus 20 I0. Okay. So we need the ratio of VAB and IAB. So we can see that VAB upon IAB is equals to V0 plus 20 I0 divided by 0.1 V0 minus 0.1 I0. So to find out the ratio, we only need the relationship between V0 and I0 so that we can find the ratio of VAB upon IAB. Okay. So let me paste the figure again. Okay. Here we have VAB and here we have current IA. Okay. Now, and here also the current should be IAB. Okay. So since the incoming current here is I0, the incoming current here will be IAB minus I0. The incoming current will be IAB minus I0. Okay. Now let us apply KVL in this loop, because we need one more equation to find out the relationship between V0 and I0. Okay. So KVL in this loop. So let us say this is A, B, this is C, and this is D. So KVL A, B, C, D, A. So A to B it is 0. B to C it is, since the current is I0, resistance is 20 ohms, so 20 I0 plus minus. From C to D it is minus 2 V0 because we are entering from minus terminal. Okay. And from D to A, since we can see that the current in this branch, okay, is in this direction, that is, okay, the current in this branch here is IAB minus I0. Okay, and we are going from D to A, the drop is plus to minus, A to, so we are entering from the minus terminal, so it is minus times of 40 IAB minus I0 is equals to 0. Okay, so from here we can see that 20 I0 minus 2 V0 minus 40 IAB plus 40 I0 is equals to 0. So it is 60 I0 minus 2 V0 minus 40 IAB is equals to 0. Now putting IAB from the equation number 1, this is equation number 2. So equation number 1 can also be written as IAB is equals to 0.1 V0 minus 0.1 I0. So 60 I0 minus 2 V0 minus 40 0.1 sorry minus 0.1 I0 is equals to 0. 60 I0 minus 2 V0 minus 4 V0 plus 4 I0 is equals to 0. So 64 I0 is equals to 6 V0, or we can see that V0 is equals to 64 divided by 6 I0. Okay, now putting this in this equation number 4, we can say that VAB upon IAB is equals to 0.1 V naught minus 0.1 I naught, and the numerator was V naught plus 20 I naught. Okay, so I have to add one more page here. Okay, so V naught is equals to 64 upon 6, that is approximately equals to 10.6 approximately. So we can easily put the value that is here. We can see that it is equals to 30.6 I naught divided by 1.06 minus 0.1 I naught. That will come out to be 30.6 divided by, if you subtract 1.06 minus 0.1, it will come out to be 0.96. So 30.6 divided by 0.96, it will come out to be 31.8 something. Okay, so this is the solution to the problem. Okay, now let's come on to the last problem. We have to find out the Norton equivalent at terminals A and B for the circuit in the figure. Okay, so first of all, let me copy the figure. So first of all, we have to find out the IN current. So to find out IN, we will short circuit the terminals between A and B and let the current here is IN. Okay. Okay. The circuit has one independent source, so IN will not be 0. So let us calculate it. Okay. Since here it is short circuited, we can see that the current in this branch will be IN. The incoming current at this node is 2. The outgoing current at this node is I naught. So this is node A. At node A, the incoming current is 2. The outgoing current is IN and I naught. Is it okay? Now we have to find out the value of IN. So we need one more equation. So let us apply KVL in this loop. Okay, so let us say that this is A, B, C, D, E. So KVL loop A, B, C, D, E, A. So A to B, the drop is 10 I naught. We are entering from the positive. Here the current in 2 ohm resistance is IN and it is flowing from left to right, so it is plus minus. So plus 2 IN. C to D it is 0. D to E it is 0. E to A, since it is plus minus, current is from top to bottom, I naught current is flowing. So we are entering from the negative terminal. So it is minus 4 I naught is equals to 0. So from here we can see that 6 I naught is equals to minus 2 IN, or we can say IN is equals to minus 3 I naught. Okay, so we can easily solve and we can get that this implies, so putting this in equation number 1, we can see that I naught equals to minus IN by 3. So putting this in equation number 1, we can say that 2 is equals to IN plus I naught. So it is IN minus IN by 3. This implies 2 IN by 3 is equals to 2. So IN comes out to be 3 amperes. So the Norton equivalent current is 3 amperes. Okay. So IN is equal to 3 amperes. Now let us solve for RTH, or we solve for RN. Method is same. Okay. Now to solve for RN, we will first of all open circuit this current source. We will remove it. Open circuit the current source. Okay. And since there is a dependent source, we will apply a voltage V0, and we assume that the current here is I0 to find RN or RTH. They are same. Okay. So we will remove the independent current source by open circuiting it, and since there is a dependent source here, we will apply a voltage V0 and current is I0 from it. Now here we can see that, sorry, we are not looking at I0, we will use it VAB and IAB. Okay. So the current here is IAB. So since no current can flow in here, so the no current can flow in this branch because it is open circuited. So the current I0 here will be equals to IAB. Okay, so let's apply KVL in this loop. So this is B, this is A, this is C, this is D, E. Okay, so A, C, D, E, B, A. Okay, now from A to C we can see that since the current is flowing from right to left, so we are entering from the positive terminal. The drop is 2IAB. From C to D we are entering from the negative terminal. The drop is 10I0, so minus 10I0. From D to E, plus minus, the drop is 4I0. From C to B it is 0. Sorry, E to B it is 0. B to A it is minus VAB. Now as we know that in this case I0 equals to IAB, so we can see that it is 2IAB minus 10IAB plus 4IAB is equals to VAB. Okay, so we can say that VAB is equals to minus 4IAB. This implies the RTH is equals to minus 4. That is, there is a negative resistance case. Okay, so since IN is equals to 3 and RTH equals to minus 4, so the equivalent is 3 minus 4. Okay, so this is the equivalent of the circuit. Okay, so we have solved all these 4 questions. I hope that Thevenin and Norton theorems are very much clear to you and you can solve all the questions related to it. Okay, so thank you students. Keep sharing these lectures and give us the feedback.